welcome to Module 50, where we introduce the idea of clustering, and we're going to use clustering with the k-means algorithm in particular. So by the end of this module, you ought to be able to explain in plain language what clustering is and how k-means form as clusters. You ought to be able to write k-means objective functions and walk through the assignment update iteration. It's an iterative method. You ought to be able to implement k-means in scikit-learn with and without feature scaling, which will be a big component of this module. You ought to be able to diagnose when feature scales and outliers are distorted or distorting the results. And you should be able to reflect on the risks of clustering people, individuals from the ethical point of view. So far, not all, but a lot of our analysis, especially when it came to things like k-nearest neighbors and classification and regression, we always had labels. So in the classification sense, you might have a label like, this patient has this diagnosis, and we can try to predict that given certain inputs. In the case of regression, again, from a healthcare context, you might want to predict something on a scale, like given the same sort of information, maybe some additional input information, try to predict how many days it'll take until this person might be readmitted to the hospital, if at all. Right? That's a regression task. Very similar, both machine learning tasks, both mapping inputs to outputs, especially from the case of what we're talking about. So we can kind of flip the question, or in fact not flip the question exactly, but just like shift gears entirely. So what if we only had the input features? We had no labels. So we didn't know the diagnosis, we didn't know how many days until readmission. Maybe we would like to predict something that is just not labelable. We don't even know what it is that we're trying to label. We're just kind of exploring the data and for a new phenomenon or a new task or scenario. And we just want to discover the structure in the first case, right? There's some kind of structure we know exists, but we don't know what it is, and we're going to try to use some data science methods to help us locate it. So now we have the idea of unsupervised learning, whereas supervised learning would provide the ground truth for classification or regression. We don't have the output anymore. We still have input, we still have the feature vectors. We don't know what the, quote, right answers are. We don't know what we're trying to aim towards or predict. But we can still try to find patterns that could be useful to help us understand the nature of the data. Maybe, if we can segment the data, this will help us in thinking about how to design interventions to take in the real world. And maybe it'll be helpful to build downstream models, or even just as components of larger architectures. I think at the penultimate slide, or near the end of this module, I'll mention a couple of instances where like the deepest neural networks, well, not the deepest, but very modern deep neural networks being applied to relatively complicated tasks still have components where they use the kind of clustering we'll be talking about today. So clustering is one of the main unsupervised tasks. There are other ways that we can do unsupervised learning, but clustering is often what we think of when we think of unsupervised learning. We have a lot of points in kind of real valued space, like we've had throughout much of this course, and we want to just kind of group them into subsets that seem to be somewhat similar. So we're going to focus mostly on an algorithm called k-means clustering, but we're also going to experiment a little bit with how scaling, data scaling, which keeps on coming up in this course, can change the story of our analysis. So let's scaffold our concepts. Just some definitions. So clustering is when we have n data points, x sub 1 to x sub n. Each of these data points is a d-dimensional real-valued vector. And we want to find how to zoom out of this camera using this handy little tool. There we go. So given all of these d-dimensional points, we want to find groups, or what we call clusters, such that the points that are within what we call a cluster are similar or close to each other in some way, and the points that are in different clusters are less similar or farther apart from one another. So we need to have this concept of well, I guess labels that we're going to automatically assign, and also we need the concept of similarity. K-means clustering in particular, we're going to choose a number of clusters beforehand. We're going to choose it ourselves. This is going to be called k, and this is a hyperparameter. So you'll remember from previous modules, a hyperparameter is just like a variable that has an effect on the learning process, but is not learned automatically in the default learning process. I'm going to mention a little bit later how we can optimize this hyperparameter using data and experimentation, but generally the idea is we'll choose this manually. The k-means clustering algorithm will find clustering centers, or centroids, which is a nice nerdy sounding word, which I like. The centroids will borrow the variable from means. It's a similar concept, but confusingly it's not exactly the same thing. But these centroids are called mu, like mu sub 1, mu sub 2, all the way to mu sub k. We have k of these centroids, one per cluster. We will also assign every point in the entire data set, x sub I, or at least the training set, which we can still have in unsupervised learning, to one cluster. So the cluster will be this label z sub I. It'll be 1 or 2 or 3 or 4. So z sub I is the cluster label we apply to point x sub I. So every point will have a cluster label assigned to it, and that label will come from the set 1 to k. Our objective, kind of roughly, is we want to put the points with similar neighbors and place every centroid in the middle of that cluster. So a bit more definitionally, a centroid is just the mean vector of the points currently in a cluster. Say mu sub j is the centroid for the jth cluster. So for all of the data points x sub I that are in the jth cluster, as you can see down here at the bottom of the sum, we just take the average of all of their points, right? So we sum up all of those vectors, and then we divide by the number of data points in that cluster. So C sub j is the cluster, and this bar on either side just means the count, the cardinality of that cluster, so the total number of points in that cluster. All right, so pretty straightforward. Technically, we have this measure called the within cluster sum of squares, or WCSS. This is, technically it's the correct term, but I kind of prefer the term distortion. So even though I'm usually going to write WCSS, I'm going to refer to this as distortion, which is another name for the same thing. The distortion measures the total square distance from every point to its cluster center. So here we have like the sum over all of our data points n. What is the distance between x sub I and the cluster to which it belongs? Well, z sub I is the cluster to which it belongs. Mu sub z sub I is the centroid of the cluster to which x sub I belongs. We'll just find the difference between these and square it, and then we'll just sum it up. So this isn't the average of the sum of squared differences. It's just the sum of squared differences. K-means is going to try to minimize this. We want all of our data points, x sub I, to be as close to their respective centroids as possible. This kind of satisfies the first informal criterion we mentioned earlier here, which is that the points within a cluster should be similar or close, which I'm highlighting at the top over here. So what is k-means doing? Well, here we have our original points. This is very cartoonish, right? Because like normally the clusters aren't so segmented in this way. But here you can see there seems to be 3 kind of groups, but each of these data points, there's no label assigned to it. I have an annual spend in dollars. I have the visits per month. This is like a data set we might find in like a consumer-facing company. So we have values of x. So we have a 2-dimensional vector x, which represents annual spend and visits per month. We don't have any labels, but there seems to be, like for each of these data points, each representing a different customer, there seems to be 3 different customer groups, right? So this kind of group down here doesn't spend very much per month, well, relatively, and it doesn't visit too much either. But then as you go towards the right, they spend more and they visit more. So after k-means, so we're skipping a step here, obviously. After k-means, we've decided that k equals 3, and then you're going to end up with these 3 clusters now colored. Every color represents the label for these clusters we've automatically determined, and these big white X's represent the centroids of these clusters. I've drawn in kind of lines from some of these points to their respective cluster as well, just to emphasize that we're measuring distance here. One thing to just make clear over here, if it wasn't already, is that the centroid, even though it's a vector that kind of sits among all of the data points in that cluster, it isn't one of the data point itself, right? So the centroid can be a vector in the same space, but it's not one of the original data points. It's kind of floating among the other data points. So here we just want to do a quick thing. We have the k-means on the raw features. Nothing really new here. It's just kind of, I'm just squishing things, but it's the same data. But we can also do z-scoring. So we z-score visits per month, and we z-score annual spend independently. We get, that those data are now going to be centered around 0 respectively and have standard deviations of 1. We've seen this already. We can do a k-means clustering there also. So far, there doesn't seem to be any difference between these two clusterings, which is good. We're going to see some examples later where things can get a little bit funky. So a little bit of math, but very light. This is a very simple concept. So again, in k-means, we want to assign the data points to cluster labels, and we want to find centroids. And we want to do this in order to minimize the distortion, the within cluster sum of squares, right? So we want to minimize, we want to choose mu and the labeling such that this sum from earlier is minimized. This is actually a hard optimization problem. It's non-convex, so we can't just kind of zoom down to a global optimum through use of gradients like we've seen in previous examples in this course. In fact, it's combinatorial, and I'll explain a little bit of what that is a bit later. We're not going to search all possible assignments. That's going to be like far too costly, but we can use a greedy alternating algorithm. You'll find a lot of algorithms in computer science. They use this greedy approach where, given a particular state, they'll just change to the next state in a way that optimizes some criterion. Similar to gradient descent, but often in a way that's kind of heuristic, like it's a rule of thumb. It doesn't necessarily guarantee anything, but it's generally it works fairly well. In fact, there is a guarantee associated with this greedy problem. I'll mention that a bit later, but it's not always the case. So Lloyd's algorithm, I'm probably not going to use the word Lloyd's algorithm too much, because normally when people talk about k-means clustering, they implicitly mean Lloyd's algorithm. But the idea here is first we just do initialization. So we can initialize the centroids totally randomly. Within the entire range of where the data lie, we could sample random points, and those can be our initial centroids. So that those points don't necessarily have to come from our original data either. Sometimes that's dispreferred, just because sometimes you can randomly sample in this space these centroids that are far away from real data. So a preferred approach, and an approach I tend to take when I'm doing k-means, is to randomly select without replacement, and without replacement is important, actual data points from the actual data set. This guarantees that you're starting with centroids that are close to the actual data because they're sampled from the original data. So you take k different random points in your original data, and that's your initial centroids. These are going to move around through the process. We do it without replacement because if you do a replacement, there's a slight chance that you'll sample the same point again, and then you're going to have two centroids starting at the same point, and then the way the algorithm works is that they'll never be able to change, and you're going to end up with k-1 clusters instead of k. Not the best approach. And there are other approaches to random initialization. Like many random processes and greedy processes in particular, like the randomness plays a big role in the end results. We've seen this several times, even with the random seeds we use for random number generation. How we initialize does play an important part. We're going to see a little bit later a quick hack that lets us get around, possible problems associated with that initial randomization. So then we have just two basic steps. We have an assignment step and an update step. The assignment step is completely easy. This is just for every data point x sub I, we just label it with its closest centroid. So we have our J being one of our k clusters, one of our k centroids. We'll just find which of the centroids is closest to the data point x sub I care about right now. So I have my sum of I have my squared difference, which is like the Euclidean distance, like the straight line distance. And then this gives me the label. So Z sub I is just the cluster index or identity associated with that centroid. So now every data point is somehow colored with the color of the cluster, so to speak. You don't need to use colors, but I'm just using it for simplicity. And then we update. So then for every cluster J, you're going to recompute its centroid as the mean of all of the points that were assigned to it. So every data point x sub I now is now part of a cluster. I'm going to just take the silos, each of those clusters, separately. Within every cluster, see for every I in cluster J, just take the average of all the points in that cluster. So sum over all of their values and then divide by the number of data points in that cluster. That gives me the new centroid mu sub j. This kind of follows the definition from earlier, right? This is pretty straightforward, right? So I have some centroids already existing, which I've initialized. I'll just find out, what the clusters are so far. So I can do that by just assigning every data point to its associated cluster through its nearest centroid, and then I'll just recompute where the average should be, which will shift the centroid over a little bit to the actual mean of all of its component data points. And then I'll keep on going. So this is an iterative process. Because I've shifted the centroids over a little bit, I might have lost a couple of data points that were previously in my cluster. Maybe now they're too far away and they're part of some other cluster. I'm speaking as a centroid right now. And maybe I've moved towards other data points that previously weren't part of my cluster, but now are very close to me, so I've gobbled them up and now they're part of my cluster. So I have different data points that are part of my cluster, therefore the average of all of this new set of data points that are part of my cluster will have a different average, so I just change my average to that new point in space, and I iterate until either of two things happen. Either the assignments stop changing, so I'm at a point where the labels on successive iterations of the algorithm don't change. Maybe I hit a maximum number of iterations. I tell the algorithm stop after 1,000 or something iterations, and then you stop at that point. Maybe you stop after the total distortion also stops decreasing a certain amount. That's a bit harder to intuit beforehand, but that's a common way of stopping. So a couple of quick facts. This is what I mentioned before about a guarantee. The way that Lloyd's algorithm works is that whenever you assign, after every assignment step and every update step, you're never going to increase the total distortion that we computed a few moments ago. So as long as you pick the closest centroid during the assignment phase, and as long as you take the mean of all of the points that you've assigned to that centroid in the assignment phase, using the sum of square distances, the distortion will always decrease. So you'll always get points being closer and closer on average to their respective centroids. Or it will remain the same, but it's never going to increase. You're never going to have two subsequent iterations where the total distortion gets worse or gets larger. But because there are many, only so many possible assignments, the algorithm will converge, so you're guaranteed to end at some point eventually. That eventuality might be very far in the future, which is why we might cut off after a certain number of iterations. The problem is, because we're starting with a random state, a random set of initial centroids, you might end up in a local minimum. You might end up converging on a set of final centroids that are better in some sense than all the previous iterations of the algorithm, but are not necessarily the best set of centroids globally, the best set of centroids you could have possibly found for this particular data set. And that's because you started off in random places in state space, a random initial assignment of centroids. So different initializations can give different solutions. I'd advise you to go ahead and experiment with that as much as you possibly can, just to get a sense of it realistically. In sklearn, we have this algorithm called k-means, which we'll see a bit. The documentation's right here, and there's an attribute called ninit. This basically controls the number of iterations we can run. So we'll run this whole process ninit number of times. We'll have the total distortion for the final set of centroids for each of these ninit runs of the algorithm, and we can just therefore pick the centroids that has the lowest distortion at the end of the training process, after the end of these ninit attempts at the training process with the n init different initial centroids. We have one more thing to mention, just a measure of goodness. There's many measures of goodness. We're only going to talk about one just for simplicity. The silhouette score is the most basic of these. This is basically a measure of how separated the clusters are from one another. So we know that there's a sort of geometry to k-means, and we want to use this as sort of a sanity check. So the silhouette score is internal metric. We might call this an endogenous metric. Or an intrinsic metric, regardless of what we'd call it. It's pretty straightforward. Roughly, it's the idea of measuring for every point. I'm speaking as the point now, am I closer to my own cluster than to any other cluster? We need to measure this deterministically. So for a given data point I, A sub I is the average distance from I, us, the data point, to all other points in the same cluster. And B is the smallest average distance from I to any other cluster. Okay, so here we have this point I, and we're measuring the average distance to all of the neighbors in my blue cluster. That's A sub I. There's many iterations of this. Sometimes you measure every single data point in your cluster. Sometimes you only find the nearest neighbors and measure the average distance to those. But the same idea holds. Let's just for now say it's for every point in your cluster. Now you have the average distance to all of the data points in another cluster. So here, these arrows here are the distances to all the data points in another cluster, the orange cluster. And again, you might compute the average distance to all of the points in this orange cluster. You could also measure the distance between me, I, and all of the data points in some other cluster, this gray cluster, C over here. So we're going to have like a couple of different B's to choose from. We want to choose the smallest of these. I suspect, looking at the graph, that it might be the C cluster that's closer to me, point I, than the points in cluster B, but that's as maybe. But you can compare this. So if A sub I, if A of I is much smaller than B of I, then I is tightly within my own cluster. I'm way closer to my neighbors in my community, my blue community, than I am to the orange community. So that seems to indicate that the clustering process did a good job. If A of I and B of I are pretty close to each other, that might suggest that I'm pretty close to the boundary between these two clusters. I'm just as close to all of the points in my cluster blue as I am to all the points in the other cluster, say orange. Maybe an I that's somewhere here where I'm indicating will roughly be the same distance to each of these clusters. So A of I and B of I will be the same. If A of I is bigger than B of I, then I've been assigned to the blue cluster. Maybe I'm closer to the blue centroid than I am to the orange centroid, so that's fine, it worked. But I am, on average, closer to all of the points in the orange cluster than I am to the points in the blue cluster. So that's a little bit funky. So in this little worked example, A of I is 0.55, B of I is 3.81. The average distance to points in my cluster is far less than the average distance to the points in the orange cluster, so everything seems good. I have to go one step further to actually define the silhouette value, though. So putting a box around it, the silhouette value is S of I, S for silhouette. That's just the difference between B of I and A of I. I hope B of I is bigger, so I hope the numerator here is positive, divided by whatever of these two things is bigger, just for normalization purposes. So again, A of I and B of I is as we've defined it previously. I'm not going to prove this, but you can do it yourself if you want. S of I, the silhouette score, will always be between -1 and +1. In fact, just for your own sake, you might want to just flex your muscle a little bit and prove to yourself that this is the case. But S of I is this score. We might look at the average silhouette score over all of the points. So for all of the n data points in our data set, we take its silhouette score. We compute this for every single point and take its average. This is the measured average of the silhouette scores in our entire data set. If the average is less than 0.1, this might indicate weak or overlapping clusters. So like the A's and B's are pretty close to each other. So like on average, these clusters seem to be kind of very similar. This isn't, again, I'm not measuring the performance of k-means now. Like k-means did its thing kind of very mechanistically. This is more of a measure of the nature of the clusters I found themselves. If I'm trying to describe something that I found in terms of the reality of the data distributions, I can use the silhouette score to kind of numerically or quantitatively tell me something about the nature of these clusters. So if S bar over here, the average silhouette score is pretty low, I can say that, well, I haven't really found really distinct clusters here. Therefore, I haven't found, distinct customer groups, going back to the earlier example. Again, if the average silhouette score is between 0.2 and 0.5, these might be a reasonable structure, and if the average silhouette score is above 0.5, these clusters are very clearly separated. Again, this might be for very simple cases that aren't very realistic in terms of real data. There we have it. I want to point out that these numbers are just rules of thumb, so like so many other things in statistics, at some point we'd end up to this point where we just use tradition and we just use heuristics like this. But these numbers weren't engraved in these golden tablets brought down from the mountain, so don't necessarily put too much belief into any of these numbers. You can see some more documentation here at how sklearn implements the silhouette score. You're going to pass in the feature matrix, like the raw data X. Usually you'll scale this first, and you'll also pass in the cluster labels so you can measure A of I and B of I and so on at all. So a quick little anti-example. Imagine you have data for hospital, you have their age, the systolic BP, the home postal code, diagnostic code, the risk score coming from labs you got back from the lab. And you're going to feed all of these columns directly into k-means clustering using Euclidean distance, which is what we've been using, the squared distances, the two norms, on the columns. So what's wrong with this? So k-means assumes that everything is numeric, right? So every variable that you're getting is numeric, so you can measure Euclidean distances. But if you have things like strings or categories, then these aren't going to be meaningful in this geometry. We talked a little bit, you can go back into previous modules looking at one-hot encodings, and we talked about why having nominal categories that might be transformed into numbers. So diagnostics code might technically be an integer, and therefore you can technically put them on a line. But the actual meanings of those numbers don't obey the laws of geometry, so we'd maybe convert the diagnostic code into some other vector using one-hot encoding. We talked about that before. But still, this is not like a numerical space, so the distances, even between one-hot encodings, might not necessarily embed distances in the way that we'd expect in purely real-valued data. So there's that. There's the issue that we have huge valued scales like lab scores and age that can dominate distances. You might have other weird encodings. In fact, another thing I'd mention also is that if you're trying to find unique patients, well, you already have the diagnostic code, so maybe you shouldn't even be doing unsupervised learning at all. Maybe what you really want to be doing is supervised learning and using diagnostic code as the outputs Y you're trying to predict. But that's also as maybe. So in general, you might want to restrict the meaningful numeric features and not use features that aren't going to be relevant to you. You ought to scale the features like we saw earlier using z-score normalization or standardization. You want to check whether the data is roughly spherical or not. This is a topic that's outside of the scope of this module just because of timing. But you're going to find that sometimes clusters have weird shapes, like they're shaped like moons, or they're shaped like non-linear things like S's. And different clusters that are obviously different groups can still kind of not overlap exactly, but kind of bite into each other, like two moons kind of biting into each other. K-means clustering fails at these non-spherical tasks. So just like everything else, K-means is not a silver bullet. It's not going to solve all of their problems. So again, outside of the scope of this class, but something to think about when you're famous data scientists. So the anti-example suggests several things. K-means is not a magic find groups button. You can't just flip a switch and all of a sudden your groups are there. It relies on a lot of assumptions, and you should always do the pre-processing steps beforehand as well. So a couple of quick examples. Let's look at some toy customer segments initially. So we have a very small customer data set. We have annual spend and visits per month, like we saw earlier, and we want to see if we can find k equals 3 customer segments. So nothing new here. We're just using random number generation from Python modules to synthesize these different groups. And then we just stack them all together, and then I'm just going to show you the first few of them to get a sense of what the data look like. Then we can use k-means. I'm just jumping right into it. I'm going to use the k-means function, which comes from sklearn cluster, okay? Which you've already know that because you saw the documentation from a previous slide. So what do I pass? I pass the number of clusters. This is a hyperparameter. I assume I know this already, so I'm going to say look for 3 clusters here. Perform Lloyd's algorithm 10 times, I say, and then we're going to choose the final clusters that have the lowest overall distortion. And also the random state is 1109, our favorite number for this class. Okay, so this is our k-means object. This is where I actually fit it. So, I mean, you can do 2 things. So you can, in sklearn, you can have a fit function, and then you can have a predict function, or you could do both at the same time. So here we're doing both at the same time. This data frame is our input variables x. There's no output y we're trying to predict. But we're going to assign each of these data points into a cluster, into z sub j for each of our k clusters. And then I'm just going to draw it out using our nice pandas library. So here are the clusters. Here's the means, the centroids for each of these. So the centroid for cluster 0 has an annual spend of almost $1,500 and about 4 visits per month, and so on. And here we can plot it out. So we saw something very similar to this before. This looks good because we designed our features synthetically such that we'd end up with this scenario. But we're going to poke around a little bit until we can break things, as you always should do. You should always try to break things to see how they work. So let's distort the scaling a little bit. So imagine you do something which is very common, which is say, well, like all of the data for spend is in thousands of dollars. Why am I using raw dollars here? Maybe I should be simplifying things and just using converting raw dollars to thousands of dollars. So the main thing happening here, as you can see from line 2, is that I'm taking the annual spend and just dividing it by 1,000, and I'm storing it in this new column, annual spend k. So instead of saying 1495 or 1,495, it's now 1.495 in terms of a spend. And then everything else is the same. I do k-means clustering, the same parameters as before, exactly the same. I use the same fit and predict to find the new clustering. And then I just go ahead and group like I did before. Nothing new. So now I have my new means with this new variable, which all I did was I just scaled things because everything was on the thousands, and I'm used to seeing visualizations where things are in the thousands of something or the millions of something. So I didn't seem to do anything too weird, but look what happens. When I did this very simple step, and I'm just plotting things out like before, now my clusters are all broken. So like this, you can see it for yourself, like all these data points which were previously in the turquoise cluster now are clustered with the yellow cluster. I mean, this is a bit, I tried to scale things so that like you see from 0 to 9 in both dimensions, but the things are distorted because of the scale of the graph here. But yeah, this point over here, this turquoise point, is actually closer to this turquoise centroid than it is to the yellow centroid down here. Okay, so I'm getting very different results than I did previously, even for this super toy example. And this is there to highlight the fact that sometimes you do things with good intentions and things that don't seem to have any obvious detriment to them, but doing so ends up distorting your findings. And therefore, if they distort your findings, then you're going to draw different conclusions from your visualizations from your results, and then therefore have bad interventions, et cetera, et cetera. So yeah, why did this happen? One feature's range was tiny relative to the other. So distances were dominated by the larger scale feature. Here these two variables contributed less, and modifying one kind of distorted things, and we ended up with a very different scenario. Not great. But to the rescue is standard scalar. So we use standard scalar quite a lot, and so far usually it does the right thing, so we're satisfied. But just take into consideration the fact that it may not always work. It's not a silver bullet like everything else. Regardless, we're going to use sklearn's pipeline. Say always scale the variables and then do k-means. This is our pipeline. Once we've defined the pipeline, we can go ahead and use the pipeline. We can call the fit predict on it. We get our cluster scaled, and we get our results. And here they are. And here's our good results again at the end. Let's see, we're doing anything nice here. Like one thing I should mention is that in this graph, I've kind of inverse transformed the centers back to the original scale for the purposes of plotting. So now annual spend is again back in dollars, visits per month is in raw counts, as opposed to the z-score normalized, zero mean, one standard deviation scales. Just because, I wanted to now emphasize again, going back to the visualization modules, that these visualizations are not just for you, they're for whoever you're going to show them to, and they might only have a very minor grasp on what z-score normalization even is, and they won't intuit what these values even mean. So you usually want to scale things back into their original scales when you describe things to your stakeholders or your end users. So that's the first thing I wanted to mention. I guess I'll leave that there for now, but that's something just to make sure you recall. So k-means is sensitive to feature scales because, like other approaches in other areas of this course, we're using Euclidean distance, like straight line distance, to measure a similarity between points. Scaling, especially standardization, can restore geometry when you need to scale, and doing so willy-nilly might break things. So standardization, or using the standard scalar, is standard for a reason. And you can end up potentially with interpretable stable clusters, which is nice. So in practice, you should use standard scalar for k-means when you're given numeric features on mixed scales, like we did in this super toy example. So second example, we're going to see some penguins. So here we have our penguins data set. There's this Palmer penguins data set from Seaborn, our visualization library. We have various features like flipper length, body mass, etc. And then we have species labels. So Adeline, Chinstrap, Gentoo. I'm just putting a link to the Linux Gentoo distribution. Gentoo is one of the great Linux distributions, which you should know about, of course, as a computer scientist. But anyway, so we do have labels. So we could take all of these features and just do supervised learning and try to predict what these clusters are. But actually what we're going to do is we're going to take the raw data, identify clusters from scratch, and then we're going to see if there's any relationship between the clusters we've identified and the true labels we know to exist in the real world. And by the way, you should play around with Gentoo. Maybe not on your primary system, and not if you value your time, but anyway. We load the data set here from the Seaborn library. It's called Penguins. We drop all of the not numbers from it just to get something clean. We're only going to look at these features for now and convert it to NumPy. Here's a subset of our features. We're going to use k equals 3 groups, and we're going to see how they line up, like I mentioned a moment ago. So nothing really here. Here I'm using my pipeline because I'm trying to do the good thing. I'm going to scale everything first because these body mass, length are on different scales. So I'm going to use the standard scalar across each of my variables automatically here. I'm going to have a k-means clustering. I'm going to set it with some predetermined hyperparameters. And then given this pipeline, go ahead and fit and predict, and then show the head here. So I'll show this. I'm going to show the head of the species, my true labels, and the clusters. This is not really useful now because there's many more data points, but so far so good. Each of the first 5 data points here are Adelie species, and they all happen to be in cluster 1. So there's no mistakes being made yet, so so far so good. And now I can go ahead and I can do this crosstab. I can compare the number, I can just sum up the number of times these different clusters are assigned with these different species. This is sort of like a confusion matrix. And so here we go. I have 30 data points in cluster 0 that were assigned to Adelie. I have 23 in cluster 0, not assigned. I have, so these are all my data points that were assigned to cluster 0. 30 of them were actually Adelie, 23 of them were Chinstrap, and 34 of them were Gentoo, and so on. So looking at this table, think and jot down, do you think this automatic clustering, without knowing any labels, rediscovered the labels well? Is this a indictment, or is this a measure of how good the algorithm was? Might this instead be measuring how clusterable the data was in the first case, right? So think about that difference for a moment. The data, live in a particular space. Various algorithms can be applied to it and can assign labels to it. Looking at this table, does that mean that the algorithm messed up and the algorithm is itself doing kind of the wrong thing and it's failing? Or could it mean that this is just a complicated problem and the clusters are overlapping quite a lot and it's not really a fault of k-means, it's a fault of the data, so to speak? Another subnote here is, do you know now of any measures you could apply to this to measure something about the goodness of the data in terms of clustering? And think to yourself, like, is this a form of supervised learning? Is it not a form of supervised learning? Think about this a little bit to make sure you're comfortable with that distinction. Here's just a visualization. So this is the coloring given the clusters, so not the coloring of the actual species. You can go into this code again and you can replace this line with a color based on the species instead of the cluster. You have to give it numbers instead of just the text, but it should be straightforward for you. And you can see these are the clusters that k-means clustering obtained. And I mean, superficially right now, you can ask yourself, are these three obviously different clusters, or is there like just one big relationship across all of these species? It seems to relate flipper length and body mass that does not differentiate these species. Go ahead and draw the species if you want to see if that's true or not, but there we go. So you can use the silhouette score as a crude metric. Here, silhouette score is something we've actually already loaded. I'm trying to find where I did load it, just for you. Here we go. So it's in sklearn metrics. The silhouette score defines this for us. So here we're running it. We're going to run it on the X-scaled penguins. So this is the result of scaling on our original data. These are all the labels that the k-means clustering algorithm obtained for that data. Therefore, because you have the data and you have the labels we assigned to it, you can measure all these average distances within clusters, between clusters, relate them to one another, compute the silhouette score, which is the average, and we get 0.476. So the interpretation here is from the earlier heuristic, is that it says that clusters are somewhat separated, but they're not perfect. So you can take an aside for a moment and ask yourself, well, now is a silhouette score a good measure of clusterability or not? This tells you something about like the distribution of the data points and their respective clusters, and it tells you something about the data points that are kind of on the border between clusters. But is that enough? So scores near 0 would have suggested overlapping or messy clusters, but as you can see here, there doesn't seem to be very much overlap anyway, which is good. So silhouette is an internal metric. I think I called it intrinsic earlier. So this is just a data first measure. You get a quantity, but is this quantity actually going to be meaningful for you? Like if you're, in the Antarctic continent and you want, I'm not sure if these penguins are all native to the Antarctic, but in fact, I'm sure some of them aren't. But yeah, like does this 0.476 mean anything to you? If you were not a data scientist and you were a penguinologist, an ornithologist who studies penguins, would this number mean anything to you, or would you be annoyed by the data scientist who told you, well, the silhouette score was 0.476? The real world translation is always going to be something that the data scientists have to think about. So in summary, we have internal metrics. We have like inertia or distortion, which we use during training. Lower is better. It'll always decrease with more clusters. It's another side note that you could try to prove yourself also if you're so inclined. We have the silhouette score, which is a measure after we've done training, after we've done learning and identified our clusters. Higher is better for silhouette scores. This is also a balance of cohesion and separation. There are other internal metrics which we don't have time to get into in this module, but you're probably going to see in later data science classes in your journey. We have domain sanity checks. So are the clusters we end up with in realistic ranges? Looking at the visualizations, you can ask yourself whether or not the clusters you end up correspond to interpretable groups. So like, are these small and light penguins versus large and heavy penguins? Is this cluster clearly a group that is not a frequent visitor versus another one that is a frequent visitor? Can you say something in the real world about the clusters you've obtained? If you run k-means many, many times with different seeds or different subsamples, do you get similar clusters, or in these n-init iterations of the algorithm, are your clusters like totally different from one another? Like the labels themselves don't matter so much. Like a particular group can be labeled 0, 1, or 2 in subsequent iterations of the algorithm. But regardless of the label, like are you finding the same clusters? And if you're not, then this is not stable, and maybe there's a problem. And again, downstream usefulness is always going to be helpful for you. I want to mention for a moment, so like K is something we chose ourselves, but you can use something called the elbow method. You can plot distortion versus K, and you can look for a point where the improvement will slow. So we expect, as you increase the number of clusters, to get lower and lower distortions. And the proof for this is outside the scope of this class, but you can get smaller and smaller distortions within clusters if you have more and more clusters. But there's not a universally correct K, and sometimes a set of clusters you found on data you currently have, your training set, those clusters might not generalize very well to new data that you didn't have during training. So you need to kind of pick the best of both worlds. You want to pick something which works well on your training data, but still generalizes. And therefore, you don't want something that doesn't overfit too much to your training data. Therefore, you don't want like too large a K. Too large a K has other problems with it also. So I think I mentioned earlier in a previous module, we can have 3 data sets. We have a training data set from which we obtain our model, like on which we run k-means. We have a test set, which we use only for evaluation at the very end. But we have a third data set, which is validation, which we use during the training process. But it's basically like we treat it like it's test, but we can use it over and over again, and we can use it to modify aspects of our algorithm. And in this case, we can use it to choose K. So we can choose K equals 1. We run the k-means algorithm with K equals 1. Then we can compute the distortion on the validation set. We can also compute it on the training set in this case. I just want to mention both just for completeness' sake. We have our distortion, and here it's measured. Now we choose K equals 2. We run the algorithm again. We can compute the distortion after training on the training set, or perhaps better on the validation set, and we store that. Here it is. And we keep on doing that over and over again for all the settings of K. And again, ideally on the validation set. If you plot it, you can see this kind of curve where things get better very quickly as you increase the number of clusters from 1 to a small number. But eventually, like adding more clusters to the fold fails to improve things dramatically. So it looks like an elbow over here. Here it is. I'm going to leave it here for now, qualitatively. So qualitatively, you can see that this is the inflection point where things seem to slow down. There are several ways that you can find this inflection point quantitatively, but I'll leave that for now. You can see where it is. There's an elbow. This is the point where things stop improving dramatically. And then I can say this is the elbow, therefore the K at that elbow is the one I'm going to choose going forward. I have 3, K equals 3 clusters in my to be used for testing. Some scaling. So before you use k-means in a data set, make sure the features are numeric and roughly continuous. They don't have to always be totally continuous, and maybe you have to do some pre-processing to ensure that that they are, that there's no missing data you can impute. You might consider one-hot encoding for categories. You might use a different clustering method, the ones we haven't really talked about today. You should use standard scalar within a pipeline. You can use min-max scalar within a pipeline if you have to. Consider outliers. So k-means clustering, as you'll note, every single data point among the n data points has to be assigned a cluster. But what if you have a data point which is so far away from all of the other data points in your training set that it doesn't make any sense to assign it to a cluster? That should be an outlier that you should ignore, right? So in some sense, I want to just not consider that data point. It's an outlier, it's something weird happened there, and I'm not going to consider it. There are caveats to that. You might not always want to throw away outliers. Maybe those things are interesting in their own way, but think about outliers. This is a topic for future modules, by the way, future classes, by the way. There's somewhat fancier clustering methods that account for outliers very nicely, but again, that's for your future. Sometimes the number of clusters you're looking for can come from prior knowledge. So if for some reason the MBAs or the marketers in your team suspect that there's 4 customer segments, then maybe that's a strong prior for k equals 4. You could select a small range and so on. There are some other initialization methods. sklearn has a default. It uses skmeans++. Do multiple runs. We talk about all of this. Clustering, by definition, is grouping, and if the data points each represent individual people, then you're, by definition, grouping people. You're grouping them as high and low value customers. You're grouping them into at-risk or not at-risk students, and so on and so on. And if you're grouping people, then this is where ethics, is really something you need to consider. So, these clusters might lead you to believe that there's some deep underlying relationship here, and you're going to fail to recognize that this could just be a weird artifact of that we're using k-means. And again, I mentioned it earlier, but like if you do many iterations and you end up with different clusters, and a data point belongs in different clusters at different iterations, then that should tell you that this algorithm is not a perfect description of the world. So it doesn't mean, you have to take this with a grain of salt, so to speak, with a degree of skepticism, of curious skepticism, curious and smart skepticism. Because if you have these clusters or these groupings, and then this leads to downstream interventions, like discounts, extra support, more scrutiny, then you're going to end up targeting and biased against or for different subgroups. So, again, always ask what these models are being used for. If it's being used in high-stakes scenarios like pricing, policing, healthcare, you have to take extra care, and I can't emphasize that enough. Again, you can also do some statistics to see if demographic groups are concentrated in undesirable clusters. And documentation is always very important. Eventually, I think we're going to start some new classes in Dalhousie that are focused on like really documentation around AI and around its use, but that's outside of the scope of our course. There's many places where k-means is used, despite its simplicity. It's used a lot in image compression and color quantization, so it's used like a cutting-edge graphics. It's used in vector quantization and signal processing and engineering. It's used in initialization in other algorithms. So a lot of machine learning algorithms that keep on coming up, like dynamic Bayes networks, sometimes they're initialized using the clusters that you obtain using k-means. And we saw Gaussian mixture models already. And I think I mentioned back then that we have to start with initial like means for our clusters, and those means can come to us from k-means clustering for Gaussian mixture models. I'll highlight for a second that like today there's maybe 2 or 3 state-of-the-art or pseudo-state-of-the-art speech recognition algorithms. Some of these are 3 or 4 years old at this point, or 5 years old at this point, or 6, or regardless of when you're viewing this. And believe it or not, these models are deep neural network transformer-based architectures, but they still use k-means clustering at important junctures of the overall algorithm. So despite its simplicity, k-means is still coming up over and over again, even in the cutting edge of relatively complex tasks like speech recognition. I want to highlight that some of my favorite clustering algorithms, like dbScan, will overcome a lot of the problems of k-means clustering, but that's outside of the scope of this class. So keep an eye out for dbScan, but if you're curious, you can go ahead and read some papers on it. Here are your quick checks as usual, and we have some literature for you to read, which I just cited a few moments ago. As always, thanks for watching. See you next time.